Namaste. Welcome to this channel at Dr.ARM's Chemistry. Friends, we were discussing electronic spectra of coordination compounds, and last time we have seen ligand field transitions. Now we will see what are the terms and term and state symbols. Today we will see the term and term symbols. Term and term state symbols. State symbols. These are very important terms with the help of which it is necessary to explain the electronic spectra of coordination compounds. Now we will see what are these terms. The term symbol, as we mean, is atomic state characterized by some terms such as S and L. So the spin, angular, that is total spin, angular momentum quantum number. So if we see, this is total spin, angular momentum quantum number. And this is total orbital angular momentum quantum number. So these two terms, or say values, actually we are using to derive this term symbol for the metal ion in which is present in the complex. So these terms are generally called Preion terms. Preion terms, because they describe individual atoms, or ions or free ligands. Their labels is the label for the term symbol, which is derived from such quantum numbers or the total values of these quantum numbers are used as labels, which are called term symbols. So the term symbol is a letter. Term symbol is a symbol in which there is a letter. So for example, we will represent this term symbol T, that is for term symbol. Then we are showing it as 2s plus 1, and here the value is given by G, 2s plus 1, and the value is given by G. So here this 2s, yes, from this is this this is, we will see this is the total spin, the total spin spin total spin of electrons, and this J, the value J is given by, this J is given by, there, that is the number of allowed J value. This indicates the number of allowed J values, which are given by 2s plus L, 2s plus L. So we will see later on the example of such symbols. Then, for example, if you see, the term symbol, for example, if you see the term symbol, say 3D, then this indicates that 3 is, if we want to calculate the spin or number of electrons, unpaired electrons, so from which we can calculate the number of unpaired electrons. So this 2s plus 1 is equal to 3. So therefore, we can show that this 2s is equal to 3 minus 1. So this is equal to 2. And when it is divided by this 2, we get s is equal to, then s is equal to 1. So here, this is the spin, total spin, and from which we can calculate the unpaired electrons. So therefore, number of unpaired electrons is equal to, when the total spin is 1. So here S is, we will show this. Here we have shown only S, but this total value is called a spin multiplicity. And we can get this S value from this spin multiplicity in this way. So the number of unpaired electrons, so when the total spin is 1, means the electrons are having plus 1/2 and plus 1/2, and plus 1/2. So we can get this total spin 1, means there should be 2 electrons. There are 2 electrons. Now the second term, that is D. D indicates the symbol, so for which we can show the values. So this say term, then value for S or L, then value for S. Then we can have this S, or this is 1, or this one indicates singlet, and here is 0, this S is 0. So this is pronounced as a singlet. This is pronounced as a singlet. So this term S is, that is the term S is derived when the value for L is equal to 0 and S is equal to 0. Then we know what are S and L values. So the total value, that is this S value is calculated as the sum of, we can show this value is calculated as the summation of these values. The S is equal to sum of values, that is S values, sum of MS values we will show. This is MS values. So when there are say two electrons, when the electrons are two, the two electrons are placed in a pair of state with, that is plus 1 up and plus 1 up, and this gives the value of S as 1. So this value is called 1. This is not this value, but spin value is called 1. But this S value, this total value is sum of this MS. Total value is sum of these MS. Now, the S value is the orbital value. Means we know that the quantum numbers we are having are M, then L, then ML, then MS. So according to exclusion principle, no two electrons in the given atom can have the same values or same set of all the four quantum numbers. And therefore, we can get, say for any given electron, there will be, say, some values. Now if we take the S subset, so if we take S subset, then we will have, say, this ML value, that is 0, and L value, MS value is also 0. So for any first electron we can have such type of value. So here S can have 0, L can have 0. So here there sometimes this L value is also 0. So L value, this L value is like this, like this. This L value is also sum of various ML values. And we know that these ML values are, we know that these are ranging from plus L through 0 to minus L. And L values, we know that the L values are equal to 0 to n minus 1. 0 to n minus 1. And n is the principal quantum number. N is the principal quantum number. And therefore, we can get these values. So, the term symbol is taken from such value. So, from this, we can say, for example, we can have the quantum number, say when this ML is equal to 2. Say when this ML is equal to 2, we can have the values plus 2, minus plus 1, 0, minus 1 and minus 2. Minus 1 and minus 2. So in such case, we can show this as the orbitals, in the form of orbitals, like this. So when we are having, say, two electrons, so these two electrons can be distributed as, say, with plus 1 up spin. Second electron goes into this another orbital. plus 1 half spin. So this electron has this ml value plus 2. This electron has ml value plus 1. If there is electron here, it will have 0. This will have minus 1. This will have minus 2. Again, if we see, for example, if we put both these electrons in the same orbital, then the L value, this L value for such configuration will be 2 plus 2, that is equal to 4 for such type of configuration. But according to exclusion principle, Pauli's exclusion principle, we cannot have such type of configuration. Therefore, we can show the distribution of electrons with parallel spin in order to obey the Pauli's exclusion principle. We have to represent these two electrons with same spin. Then we can get the value. Then we can get this L value according to this summation. So we have to sum up this L value. So here for first electron, the value is, so we separate these values like this for understanding. So this will have plus 2 values. So that is, this will have 1 value. And there is no more electron. So the total value is 3. And we have the value 3. So when we have 2 electrons, the L is equal to 3. Then if we are having the S value here, S value, what is S value? Plus 1 half, plus 1 half. So the total spin is 1. Total spin is 1. And from this S and L, we can get the term symbol. So we will understand how are these terms. So we will remove this part in order to use this space. So we will show that is this jar, then value of L and value of S. For example, the value of L is 0, this is S, then it gives L plus S is equal to this J value, that is 0, and for this term is S. The term to be used for such type of configuration, or that is atomic state or free ion state, is like this. So here S designates the atomic spin quantum number as well as a state of having L. Then we can have, say this will have 1 S, that is singlet S. We have to read it as singlet S. Then if we are having 2s, that is doublet S, the L value is 0, S value is 0. Then again if we are having, say, another value, say that is 3p, then we can have the L value 1, S value, here it is 1/2. So here it is 1/2. Then here the S value is 1. Again if we are having say 4D, the L value is 2, then S value is 3/2. Then if it is 5F, these are some examples, then it is 3 and this is 2. So if we are having the symbols like this, that is 3, so we can have the term So for this purpose, in simple words, we are giving the term symbols, that is terms. If the terms are having these values, the terms are designated with the values 0, 1, 2, 3, 4, 5, 6. So that is the L values. Then, so these are L values. So we can have their symbol like this. So for when L is equal to 0, the symbol is S. Then for L is equal to 1, the symbol is P. For L is equal to 2, the symbol is D. For L is equal to 3, the symbol is F. P, D, F, G, H, I. So in this way, so we are not using here J. So for 7th term, we are not using J because it is usually other terms, or it is used somewhere else as J. Therefore, it is not repeated here. So we are skipping that J value and using the next, that is S, P, D, F, G, H, I, K. E is also not used here. S, P, D, F, G, H, I. So here we have to explain these terms. So we have to show these terms in this way. So this is term for L. So these are having L values. So these are having L value. So here, if you find this value here, in case of, say for example, when the orbital has 2 and V2 configuration, then there are 2 electrons and these 2 electrons are distributed in this way. So this atomic state or free ion state it may be, it is designated with this L value 2 plus 1. 2 comes from this orbital, 1 comes from here, so it becomes 3. So 3 corresponds to F. So it is given by F. The term for this is coming from this, that is F. And the multiplicity, that is, this is S value, but the spin multiplicity is calculated as 2 S plus 1. So here 2 into S is 1 plus 1. So it gives 2 into 1, 2 plus 1, that is 3. So the spin multiplicity is 3. So in this way, we can get this spin state. And later on we will see the J value because it is further studied here. Now, in this way, we can get variety of uses of this term. So we have seen that we have to follow Pauli's exclusion principle in order to understand this type of deriving the term symbols or free ion terms. Now if we consider another example, so we need only this type of configuration. So if we see another example having the value like this. So another example, that is for low spin D4 ion or atom, it may be atom or ion. So when we want to consider that is the low spin state. So these are d orbitals and these are T2g, these are EG orbitals. So in case of the 4 configuration, we are first of all distributing these 3 electrons with the same spin, and the 4th electron for low spin complex we have to pair that one of that electron. So we will get this electronic state, and now from this we can derive the term symbol. So the spin multiplicity, so this is the low spin, then spin multiplicity is spin multiplicity is equal to 2s plus 1, that is equal, we know that 2, and s is, these are the 2 electrons use 0 spin, so here we produce the spin 1 plus 1 gives 3, so it gives 3. Then, so this is first state, this is second state. Now the third state is highest possible value, use highest possible values for these ml, highest possible values for ml in order to derive the h, that is term symbol. So when we are having these values, we can show here that the values are like this. We are having here 2 values. So this we will show here the ml values. So this has plus 2 plus 1 0. So there are 2 electrons. So this value for L is given by, that is ml value is given by the our first electron 2 plus second electron 2 plus third electron 1 plus fourth electron 0. So this gives 2 plus 2 4 plus 1, that is 5. That is 5. So in this way we can get this value for L, and if we go here for giving the value for F, 5, it is H. So the term is H. The term derived here is H, and therefore the term symbol, therefore the term symbol is the multiplicity, that is triplet. This is triplet. So we have to show this as 3 triplet and this term H. So we get how to read this as a triplet H. This is a triplet H. So this is for low spin configuration. Now, if we consider the same for high spin state, high spin configuration, for high spin D4 configuration, then we can show the distribution of electrons. So 3 electrons are going with same spin in order to obtain high spin complex. The 4th electron will go with same spin in each orbitals. So this is T2G. Now we can show the values which are like this. So here we can show the same values like this. So this 1, 2, 3, very end fourth value like this. And these are the L values, that is ML values. So these are ML values. So from this we can get these ML values. So this is the first step, that is configuration. Then second is spin multiplicity. Multiplicity, that is 2s plus 1, where this is 2 and yes is 1 half plus 1 half plus 1 half plus 1 half. So it gives 2 into 2, that is 4 by 2 is 2 plus 1. So it gives 2 into 2, 4 plus 1, that is 5. So spin multiplicity is 5. Then next term is the value for value of L, or sometimes it is this way is shown as this capital letter and L value. Means alternatively we can show this L or this way. This is in some books this term is used and in some books this term is used. So for this value we can get, see, this L value as by counting these values here we have shown. So 2 plus, so we will show here 2 plus 1 plus 0 minus 1. So this will be summed up as 2 because this gets cancelled and we get this 2. So this is a duplet or doublet we can see here. This is doublet. So the term symbol is arising from this value is this is here, that is quintet. This is not doublet. Here we are calculating this value in order to obtain. So the corresponding value for the term for 2 is D. So the symbol is D, and therefore the term symbol is D with the spin multiplicity 5. So in this way we can calculate the values So we have taken these few examples of the same, that is D4 configuration. Then we can also calculate the same for D6 configuration. So if we consider this for D6 configuration, then for high spin state we can get the values like this. So these are 5 plus this one. So for this sake of configuration, the values can be calculated. So we will calculate first the spin multiplicity. The number we have to find out number of unpaired electrons 4. So it is 2 into 2 means 2 into S, that is sum of spins, that is 4 plus 1. So that is also 5. So high spin configuration, the value of that is spin multiplicity is coming the same. So for D4 and D6 the value is same value. For L we can have the values. For L we can have the values. So here for D6 configuration we can have the values like this. So we have to count here. For L value, or we can say for ML values. So what is the 2 plus 2 plus 1 plus 0 plus minus 1 and minus 2. So this comes out to be, so we can so for this plus 1 we can remove this, for this minus 2 is minus, so ultimately we get this 2. So for 2 the symbol is D, for 2 symbol is D. Again the value is 5D. So for D4 and D6 the term symbol is same for high speed state. For low speed state we can find out the terms. For low speed state, low speed D6 value or low speed, the value, the 6 electrons are distributed in this way. Okay. Then the total spin here is, the total spin is 2 into 0 plus 1. So it gives 1. So this gives 1. Then we can get this term ML value by using these configurations. So we have to distribute the 6 electrons in this way. So we can show these 6 electrons in this way. And therefore the N value or ML value is coming like this: 2 plus 2 plus 1 plus 1 and plus 0 plus 0. So this is equal to 2 plus 2, 4 plus these 2, that is 6. That is 68. 6 plus 68. It will give us the symbol I. So for this, the term symbol is I, and the spin multiplicity is 1. It's 1. So this is called singlet I. This is called a singlet I. 1 for singlet. If we show here 2 doublet, 3 triplet, 4 quartet, 5 quintet, etc. So in this way we can find out the various terms. So we will stop our discussion here, and in the next lecture we will see how the Preion terms are summed up or shown for a specific electronic configuration. In this way we can use the other orbitals like s orbital, p orbitals, d orbitals. But we have to understand that the s orbital is non-degenerate and does not, it is not affected by the crystal field splitting. So the d orbital splitting is not having any impact on the splitting of s orbital. Similarly, p orbital is also not showing any impact of crystal field splitting of d orbitals, and that, or we can say ligand field of the d orbitals in the given complex. So these are not showing any crystal field splitting. Therefore we are as like shown here, there is no splitting of s and p orbitals, so they will remain unchanged. But the splitting begins with these d orbitals. So we will stop our discussion here and we will see the next point, that is about the derivation of various terms or interpretation of electronic spectra of a coordination compound in next time. So see you next time. Please subscribe if not to this channel, press like button and bell icon. So thank you very much for watching.